This is Unit 4, Lesson 4, Part 3, Related Rates. We're going to continue with our typical examples of related rates. So example 6, a right circular cylinder is changing shape. The radius is decreasing at a rate of 2 inches per second, while its height is increasing at a rate of 5 inches per second. When the radius is 4 inches and the height is 6 inches, how fast is the volume changing? So, starting with a picture, what we have here is we have a cylinder that has a radius and a height. And so we already have our known, it's given in the problem, is our volume equation, so V equals pi r squared h. The volume of any right cylinder, three-dimensional figure is always the area of the base times the height, and the base is a circle, pi r squared times h. Okay, so what are we given? We're given the rate of change of the radius. So the radius is decreasing at a rate of 2 inches per second, so that's going to be a negative 2 inches per second. And we're also given the rate of change of the height. The rate of change of the height is increasing at 5 inches per second. And we want to find out what happens when the radius is 4, and so that's inches, and the height is 6 inches. So we're pretty much ready to go. We want to know how fast the volume is changing. So we want to find dV dt, and we want to remember what kind of units we're looking for. Volume is three-dimensional, so it'll be cubic inches per second. So we want to make sure at the end we're multiplying 3 linear measurements together to get the cubic, and we have it per time. All right, so let's start with our equation and start by taking the derivative with respect to time. Okay, so we have V equals pi r squared h, and we're going to take the derivative with respect to time on both sides. That just looks really horrible. Let me rewrite that. Now, we're going to have to use a chain rule like we always do with taking the derivative with respect to time, but we also have a product here, so we'll have to use our product rule as well. So what we're going to have is we're going to have dV dt is going to equal, and I'm just going to leave the pi. I mean, I could pull the pi out, but I'm just going to leave it there, I think. I'm going to take 2 pi r h times dr dt. Okay, that's for taking the derivative of r with respect to t. And then plus, I'm going to keep my pi r squared, and then the derivative of h is going to be dh dt. All right, the nice thing is for this one is we don't have to solve for everything. We can just fill in all our numbers. So dV dt, when r is 4 and h is 6, becomes this equation. 2 times pi times 4 inches times 6 inches times my rate, which is negative 2 inches per second for the radius. And if you notice here, I have cubic inches, 1, 2, 3, and 1 rate per second. So that's great. And I'm going to add to that pi times 4 inches squared times my rate for the change in the height, and that is positive 5 inches per second. And again, checking my units, I have inches squared and inches and 1 rate, so that's good. I guess I'm running out of space there. So I will just continue up this way. So that's going to give me dV dt is going to equal, I'm going to factor out the pi now. And I'm going to have 2 times 4 times 6. Well, actually, I'm going to have 8 times 6 times -2. So I'm going to have negative 96 cubic inches per second plus, and I have 16 times 5, which is 80. So my final answer, dV dt, is going to be negative 16 pi cubic inches per second. All right, next example. Now we have an inverted cone. Our inverted cone is leaking water at a rate of 1 cubic centimeter per minute. So looking at the units, what we can see here, because these units are cubic, this is my rate of change of my volume. The cone has a height of 9 centimeters and a diameter of 6 centimeters. So they're kind of hiding the radius in here. It'll be half of that. Find the rate at which the water level is dropping when h is 3 centimeters. Okay, so volume of a cone is 1/3 pi r squared h. So it's 1/3 the volume of a cylinder. So here is our cone. We're drawing it upside down because it's inverted, like that. And we are given a diameter. This is my D. Looks like an it. Okay, and then we're also given a height, H. Okay, so the trick to this one, I didn't want to give you one exactly like the last one, is we're not given what the diameter is when the height is 3. We're only given the original ratio of height to diameter. Now, if this is going to be the same cone, that is going to stay the same. Okay? So, how we're going to find this is that we know our equation, so let's just write everything down. Let me not get ahead of the solving process. We are given that we have dV dt, which is, and it's leaking, so the volume's getting smaller, -1 cubic centimeter per minute. We also have a radius of 3 and a height of, so I'll call that R0 and H0, a height of 9 centimeters. And then we also have our H that we want is 3 centimeters. Okay, so we need to find the rate of change, the level of the water. It says level right there. So that is dH dt. So what we don't have any information about is the rate of change of the radius or the value of the radius. So the idea is we want to eliminate that from our formula. So that's where we're going to start. We're going to start by looking at the fact that R over H when we start is going to be 3 over 9. Okay, so that we can think of our radius as being 1/3 of our height. Okay, because we started at 9 and then, okay, so we're going to start by coming up with a way to eliminate R out of our equation. So what we want to look at is the fact that H when we start is 9 and that R when we start is 3. So if the height is 3 times as big as the radius, okay, so what we can do is just use that relationship because it has to stay that way in order to keep it the same cone. So we can replace R with H over 3. So now what we can do is rewrite our formula this way. So V is going to equal 1/3 pi h over 3 squared times h. Okay? So simplifying that, we get a volume of pi over 27, because we have a 3 here and we'll have a 9 there. And now we're going to have h squared and h, so h to the third. So now we're ready to take the derivative, because now we have all the information we're going to need to find the rate of change of h. Okay, so dv dt is going to equal my pi over 27 times, using my chain rule, 3h squared dh dt. And now I can fill all the information. I guess I can call this step 3. So I have -1 cubic centimeters per minute is my change in volume, is going to equal pi over 9, if I simplify that, times, and we want to know when h is 3 centimeters. And we're squaring that. And then we have our dh dt. Okay, so solving this, we get, we're going to have here a 9. So the 9s will cancel. And then we're just going to have pi centimeters squared times dh dt. So dividing both sides by that pi centimeters squared, we get a final answer of, and if you notice here, centimeters cubed becomes centimeters the first. This is gone, so I have the rate I want. So my dh dt becomes -1 over pi centimeters per minute. Okay, let's finish this up with everybody's favorite problem after you do these for a while. And there are 2 of them. They're just put together in one problem, is the lengthening shadow problem. Okay, so example 8. A lamppost is 26 feet above the sidewalk. Andy Great is a 6-foot-tall calculus teacher and is walking away from the lamp at a rate of 4 feet per second. Now remember what we said, if you're walking away from the light, your rate of change is growing. If you're walking towards the light, it gets smaller, it'll be negative. When he is 20 feet away from the lamppost, find each of the following. So the first thing is we want to know how fast is the shadow length changing. Okay, so let's label some things in our picture here. So we know that the lamppost is 26 feet tall. All right? And we have 2 things. We know right here is 6 feet. Okay? And his shadow's cast in front of him. So right here is his shadow. And I'm going to call that y. That's his shadow. And then x, I'm going to call it this part. This is his distance. I'm going to call that x. Okay? And what I do know is his rate of change of his distance is 4 feet per second. So what I don't know is his rate of change of his shadow. That's going to be what we're finding here. So we have to use similar triangles. We have 2 triangles here. We have the big one made with the lamppost down to the edge of his shadow and back. And then we have the smaller one made with his height down to his shadow and back. So we have those two similar triangles. So using those numbers, we know, using the height, we know the relationship 26 is to 6 as the whole length of the bottom, which would be x plus y, is to the length of the purple triangle, which is y. So there's our equation. Okay, so let's simplify this a little bit. So we have 13 over 3 is x plus y over y. So making this just an equation in y will be a lot easier. So 13y is equal to 3x plus 3y if I cross multiply. So 10y equals 3x. So my equation becomes simply 3/10 x. Y equals 3/10 x. So now it's going to be easier with this relationship instead of the very first one to find dy dt, because that's what we're looking for. His shadow lengthens at a rate of dy dt. Okay, so doing that, we're starting with y equals 3/10 x. So dy dt is going to equal 3/10 dx dt. So dy dt is going to be our 3/10. So we have 3/10, 3/10 times 4 feet per second. And this is being evaluated at x equals 20. Even though you don't see the 20 in the equation, but it is at that moment because that's when they define the rate of change. So dy dx is going to equal, simplify to 6/5 feet per second. Or you could say, if you wanted to write this in a statement, which I've been kind of lazy doing here in this section, his shadow grows 6 feet every 5 seconds. Okay, and then finally part 2 says, at what rate is the tip of his shadow moving? So that's just the very tip. So going back to our picture above here, the tip of the shadow is at, let me use the highlighter here, is at this point right here. So it's this entire distance that is moving. So our equation is going to be this. We're looking at the rate of change of x plus y. That's the tip, that's where the tip of the shadow is. Okay, so our change, I know we don't have a real equation, we have a relationship here, but I will get there eventually. This is going to be dx dt plus dy dt. Okay, we have these two rates, so this is just a simple addition problem. So dx dt is the rate at that he is walking away from the light. So this is the 4 feet per second. And dy dt we just found is the rate of change of his shadow. So together they're going to give us the derivative of the tip. So that will give us the derivative with respect to time of the tip of the shadow. So when we add these together, make a common denominator, so we'll have 20/4 there. So we get 20 over 5. We get 26/5 feet per second. So we can say then the tip of his shadow is increasing at a rate of 26 feet every 5 seconds. And there we have it. That's the end of our examples on related rates. We'll be doing more of these in class. So as always, if you had any questions, just bring them to class tomorrow and we will go over them.